In this video, we're going to begin section 3.5 in the book, which is called implicit differentiation. Okay, now up to this point, the functions that we've worked with have been expressed in what's called explicit form. Okay, so here's some examples of functions that are in explicit form. Now, explicit form is really just kind of fancy words for the equation has been solved for y. Okay, y is equal to f of x. Now, I'm not using function notation here, but I could. Okay, all these are in explicit form. Now, some functions are defined implicitly by a relation between x and y. Okay, here'd be some examples of equations that are written in implicit form. Okay, implicit form just simply means the equation has not been solved for y. All right, so these equations have been solved for y, these have not. Now, suppose that I were to get the top equation into explicit form. Well, that just means solve for y. Okay, so let me subtract x squared from both sides and then take the square root of both sides. Of course, I'd want the plus or minus there. Now, x squared plus y squared equals 25 would be a circle. Okay, now, a circle is not a function, right, because it's going to fail the vertical line test. But if I just had like the top half of the circle, which would be the square root of 25 minus x squared, then of course that would pass the vertical line test. Okay, negative the square root of 25 minus x squared would be the bottom half of the circle. So if I just work with the top half of the bottom half, then it would be appropriate to use function notation. That'd be fine. Okay. Otherwise, something like this. Yeah, this is an implicit form, an explicit form, but I couldn't, I wouldn't want to let y be like f of x or g of x or something like that, because for each x there's only one y. There's not a plus y and a minus y. Sometimes implicit equations are tough to get into explicit form. Okay. Something like these two equations would be really difficult to solve for y. In fact, in this one you can't. Okay, so this brings us to implicit differentiation. Implicit differentiation provides a method for finding derivatives if the relationship between two variables is not expressed as an explicit equation. Okay, now, to find the derivative of y with respect to x, or dy dx, implicitly, we differentiate x as usual and then apply the chain rule to y. By the way, the notation that is common in this section is the Leibniz notation, dy dx, or the y prime notation. I will comment on that again after we've looked at some examples here, okay, but something to keep in mind. Let's take a look at an example. Suppose that we want to find an equation of the tangent line to the graph of x squared plus y squared equal 25 at the point 4, 3. If x is 4 and y is 3, 4 squared plus 3 squared is 25. Okay, so this is one point that would be on this circle centered at the origin of radius 5. Okay, and so I've drawn a picture of that circle. And I've also drawn the tangent line, and we'd like to find the equation of that tangent line at that point 4, 3. Well, so I want to find dy dx. dy dx is the derivative, okay, and the derivative represents the slope of the graph at a particular spot. I want to first find a formula for dy dx, and then I'll plug in my x and y values to get the slope of the graph at that particular point. Well, because this equation has not been solved for y, I'd want to use implicit differentiation. Okay, I'm going to begin by taking the derivative of both sides, and the derivative of a sum is the sum of the derivatives, right? Derivative of a constant is always 0, so I'm going to have 0 on the right. Now, I'm supposed to differentiate x as usual and then apply the chain rule to y. So the derivative of x squared would be 2x. The derivative of y squared would be 2y, but I've got to apply the chain rule to y. Now what I mean by that is after you've differentiated something in terms of y, you need to tack on a dy dx. Okay? in order to finish the chain rule is what we mean by that. So now I want to find dy dx. Okay, with this equation here, let's go ahead and solve for dy dx. Let's subtract 2x from both sides and then divide by 2y. The 2's will cancel there, and so dy dx is negative x over y. Now dy dx represents the slope of the graph at any point on the graph, and I'd like to know the slope of the graph at the point 4, 3. Well, so x is 4, y is 3. I'm going to plug those numbers into my formula that I've created. Negative 4/3 would be the slope of the graph at this point 4, 3. Now that I know the slope, it's negative 4/3, and I know a point on the graph, I'll use the point slope equation here to find the equation of this line. Y minus y1 is 3 equals the slope, negative 4/3 times x minus x1 is 4. Okay, in slope-intercept form, when you add 3 to both sides, y is equal to negative 4/3 x, and then let's see, 16/3 plus 9. 9 is the same as 27/3. Let's see here. Let's see, 16/3, and then I'm adding 3. 3 is the same as 9 over 3, right? So 16/3 plus 9/3, that'd be 25/3, of course. Okay, and so that would be my answer. A couple of things. First of all, the fact that this line has a negative slope means that, when I compute dy dx, I can know very early on that the slope is going to be a negative here at this point. Okay. Now, of course, if I were to draw a tangent line, here at like 4 and negative 3, then it'd be a positive slope. Okay. Now, the way that we did the calculation is not the only method that we could have used. Okay, we could have used the previous methods here. So here's another way using the previous method. X squared plus y squared equal 25 is an implicit form. If I get that into explicit form, solve for y. We already did that earlier, right here. Okay, so y is equal to plus or minus the square root of 25 minus x squared. Now, because this point is on the top half of the circle, it would be enough to just disregard the plus minus here, since I'm only working with the top half of the circle. And of course, if I were working with the bottom half of the circle, then I'd want y to be negative the square root of 25 minus x squared. Now we can find dy dx by using the chain rule. Okay, so it's going to be 25 minus x squared to the 1/2 power. When I differentiate, I'm going to bring the power down, reduce the power by 1, and then take the derivative of 25 minus x squared, that's negative 2x. The 2's cancel, and you get negative x divided by the square root of 25 minus x squared if you write this in radical notation. Now at the point 4, 3, dy dx, well, x is 4, right? So when I plug in 4, I get negative 4 divided by the square root of 9 is 3. So I still get the same slope, negative 4/3. It's just I was able to get that using the previous methods. Okay, now sometimes you'll be able to get an equation that was in implicit form into explicit form, and sometimes not. Okay, sometimes it's going to be very tough or impossible. All right, so the idea, in a problem like this is to make sure that you're fine with implicit differentiation. Okay, and of course we'll look at some more examples here shortly. A couple more things to point out. So when I take the derivative of both sides, notice how d dx indicates that I'm going to be taking the derivative of this expression. I have not taken the derivative of this expression though. I will see students sometimes make the mistake and they'll write dy dx and then they'll have the expression to the right of that. Don't do that. We haven't taken the derivative. In other words, there's a difference between the notation dy dx and d dx. Okay, dy dx is what we want to find. D dx means that we're going to differentiate this expression, but we have not done that yet. Okay, so don't get those symbols confused. Some students will do that. Okay. The other thing to point out here is once we've found our general formula for dy dx, we want to know the equation of the tangent line at the point 4, 3. So it's important that we indicate that in the work, saying at the point 4, 3, dy dx is, whatever it is. In other words, don't just write, like over here, equals negative 4/3. Because that can be misleading if you say dy dx equals negative x over y equals negative 4/3. Because somebody can look at this and say, oh, so it really doesn't matter where we're at on the graph. You can be anywhere, and the slope anywhere is negative 4/3. No, it's not. It's only 4/3 at a specific point here, the point 4, 3. If I were working with the point 4, negative 3, or 5, 0, or something else, it's going to be a totally different result, right? So make sure that you indicate what point you're talking about, okay? Otherwise, it looks like the slope of the graph everywhere on the curve is just this one number when it's, when in fact it's not. All right, let's take a look at another example. So here's another example of an equation. This is one that I had written down earlier, this one here, okay? So here it is again. And this is in implicit form because it has not been solved for y. Okay, now I'd like us to find dy dx, or y prime. Well, let's go ahead and do that. We'll take a look at part B and part C once we have this formula here for dy dx. So I'm going to differentiate both sides. Okay, so d dx. And the derivative of a sum is the sum of the derivatives. Derivative of a difference is the difference of the derivatives. I can, split this up. The derivative of a constant is always 0. Okay, so you're going to have 0 on the right. The derivative of y cubed, well, that'd be 3y squared, but then that's in terms of y, so I got to make sure I tack on a dy dx. The derivative of y squared would be 2y dy dx. And then, of course, the constants can come out of derivatives, right? So it'd be minus 5 times the derivative of y would be dy dx. And then minus the derivative of x squared, that would be 2x. Remember, you differentiate x as usual, okay, and only apply the chain rule to things involving y. Okay, so I'm not going to put a dy dx here on this last term, okay, because this was not anything in terms of y. Now I want to find dy dx, or y prime, that's the same thing, okay? And so I'm going to go ahead and add 2x to both sides. Also, dy dx is in common to these three terms, so let's go ahead and factor that out of these three. And then, since we want dy dx to be all alone, let's go ahead and divide both sides by 3y squared plus 2y minus 5. Okay, so here would be the general formula then for dy dx. Now, part B, and by the way, it's going to be very common that you would get a formula in terms of both x and y, okay, using this particular method for differentiation, okay. Part B, find the equation, find the tangent line at the point 1, negative 3. Okay, so if x is 1 and y is negative 3, that would be a point on this graph. You could check that by plugging in the numbers if you want. So I'm going to say at the point 1, negative 3, dy dx would be what? Well, x is 1, so you're going to have 2 divided by y is negative 3. So 2 times negative 3 squared is 9, times 3 is 27, and then minus 6 is 21, minus 5 is 16. 2 over 16, reduce that, you get 1/8. So now that we know the slope of the tangent line here at this point, 1, negative 3, and we know a point on the tangent line, 1, negative 3, we use the point slope formula. Y minus negative 3 is the same as y plus 3 equals the slope, 1/8 times x minus x1 is 1. get that into slope-intercept form, distribute the 1/8 here, and then subtract 3. 1/8 x minus 1/8 minus 3. 3 is the same as 24 over 8. So negative 1 over 8 minus 24 over 8, that'd be a minus 25 over 8. And, again, make sure that your answer is in slope-intercept form, like all these other problems that we've done with equations of tangent lines. That's how the book will want it. Okay, now part C, they want us to find the tangent line at the point 1, 1. Okay, so again, if you were to plug in 1 for x and 1 for y, I can maybe quick do that. 1 plus 1 is 2, minus 5 is negative 3, minus 1 is negative 4, negative 4 equal negative 4, that's true. So this point would be on the graph. Okay, this other point would also, if you were to check. Now, if I want to find the slope of the graph at the point 1, 1, I'm going to plug in 1 for x and 1 for y. And that's going to be a problem here, right? Because 3 plus 2 is 5, minus 5 is 0 in the denominator. Y prime is undefined at the point 1, 1. Because I know I can't divide by 0. Okay, and of course, don't actually write that anywhere on the side. Don't write 2 over 0 undefined or something like that. We can't divide by 0. Okay, so it should be just an observation that we make. Hey, there's a problem in the denominator. We get 0. We know we can't do that. Undefined. Now, this graph will still have a tangent line. Of course, a vertical line has an undefined slope. So all I would do here in part C is I would just simply pick off the x value. X equal 1 would be the equation of the tangent line then. Now, they didn't ask me to do it in the problem here, but I've drawn a graph of this curve. And when you guys get into Calc 2, you'll be able to know how to get the graph of something like this better. Okay, when you talk about parametric equations, that's an option that you can use to be able to have the graphing calculator do this. You see, the problem is that this equation is not an explicit form, so it's not just a go to the calculator and punch it in type thing. Okay, I could do that if the equation was solved for y, but this one you can't solve for y. Okay. Anyway, here's the graph. Now notice that I don't have a function of x, right? Because I got something that will fail the vertical line test. But I've got some points labeled here. Here's 2 points that we had worked with. Okay, 2, 0 and negative 2, 0 would be x-intercepts on this graph. And I've drawn the tangent line at the point 1, negative 3, and also the tangent line at the point 1, 1 is a vertical line. Okay. Let's stop it right there.